So in this video, I want to talk about statically indeterminate structures and what it means for a structure to be statically indeterminate and how we can go about finding the reactions when we have this type of scenario. So basically, statically indeterminate means that you have more supports than necessary to make a system stable. So basically, your equilibrium equations aren't going to be enough to solve all of your unknown forces, and you will have to use compatibility equations, which will provide an extra equation basically on top of your equilibrium equation in order to solve for your unknowns. And basically, your compatibility equation it relates the geometry of a deformed member to the unknown forces. So it relates geometry of deformed members to unknown forces. So let's look at this figure here. So let's say we have a rod and a smaller rod that's connected to this rod, and they're in between two fixed supports. So as I mentioned before, we can remove one of these fixed supports and the structure will still be stable, even if we had this cantilever beam. We would still have a stable structure. So basically, whenever you have redundant supports, you have a statically indeterminate structure. What do we mean by relating the geometry of deformed members to unknown forces? Well, when we look at this scenario, we know that if there's some loading situation, this will deform, and the smaller rod may deform out here. However, the overall deformation will be zero because it's held in place by these two fixed supports. It can't extend out to either side of those fixed supports. So we know that the total deformation will be zero. So let's do a quick example. So let's say we had two circular rods. We had a 10 kip force there and a 10 kip force there. The length of this is 20 inches. The length of this is 18 inches. And the diameter of this is 2 inches. The diameter of this is 3 inches. And we're asked to find, let's see, we'll call this A, B, C, and we're asked to find the reaction at A, reaction at C, the axial stress in member AB, and the axial stress in member BC. And remember, axial stress is the force in that member divided by the cross-sectional area. So this will be the reaction at C. This will be the reaction at A. So the first thing I want to do is realize this is a statically indeterminate structure. Again, we have two fixed supports, meaning that we can remove one of them and the structure will still be stable. So we have a redundant support. What I'm going to do is, working from left to right, I want to find the force, the axial force in between AB and an axial force in BC. And I'll need that to apply my compatibility equation, or plug it into my compatibility equation. And my compatibility equation is going to be that the total deformation in our structure is going to be 0. So our total deformation is equal to 0, which means that the deformation in AB plus the deformation in BC, the sum of those two will equal 0. And we recall that the deformation equation is the load times the length of the member divided by the Young's modulus times the cross-sectional area. So let's find, so if we expand this equation out, it's going to be the axial force in AB, the length of AB divided by Young's modulus times the cross-sectional area of AB. Oh, and I forgot to, we have a given, the Young's modulus is known to be 0.3 times 10 to the 6 psi, pounds per square inch. So our delta BC is going to be our axial load in BC, the length of BC divided by the Young's modulus and the cross-sectional area of BC. And we'll say that the Young's modulus for both of these rods, 1 and 2, are the same. So our E1 equals E2, which equals E. So in order to find the axial force PAB, let's make a cut in between AB. We know that this is reaction at A, so this is A. And we'll get the force AB. And I always assume my forces to be in tension and let the signs work itself out. So if I do sum of the forces in the x direction, we know that's going to equal, we know that's going to equal 0. So we have minus RA plus PAB is equal to 0. So PAB is equal to the reaction at A. So in order to find PBC, we'll have to make a cut in the rod BC. This is still the reaction at A. We have 10 kips here. We have 10 kips here. Yep. And we have PBC here, assumed in tension. So let's do sum of the forces in the x. This will equal minus RA plus 20 kips plus PBC, that's equal to 0, and PBC will equal reaction at A minus 20 kips. So now we have PAB and PBC, and we can plug them into here. The length at AB is just given as 20 inches. The length at BC is given as, this is supposed to be 18 inches. So this is the length at BC. The Young's modulus is given. Cross-sectional area of AB we can find by using the given diameters, 2 inch and 3 inch. So the cross-sectional area, since we're given diameters, it's going to be pi over 4 times the diameter squared. So let's plug this into, we'll call this equation 1. So we'll plug this into equation 1. Plug in everything into equation 1. So PAB, so dt, total deformation, which is equal to 0, is equal to PAB, which is the reaction at A, length AB, which was given as 20 inches, divided by Young's modulus, which is given as 0.3 times 10 to the 6, 0.3 times 10 to the 6 pounds per square inch, so that's pounds per inch squared, times the area of AB, which is, again, pi over 4 times the diameter squared. The diameter is 2 inches. 2 squared, so this is inches squared units, plus the deflection of BC is going to be PBC, which is RA minus 20 kips. Because our Young's modulus is given in pounds, I'm going to change the kip units to pound units. So one kip is equal to 1,000 pounds. So basically I'm just going to multiply this by 1,000, so it'll be RA minus 20,000. So this will be in units of pounds now. Times the length of BC is known as 18 inches. Times 18 inches. Divided by Young's modulus, 0.3 times 10 to the 6 pounds per square inch, times the area, which is pi over 4 d squared, which the diameter is 3 inches in section BC. So 3 squared inches squared. So now I wrote all these units down just so I can show you that my units will match up. So the inch squared will cancel out. This RA is in pounds, so the pounds will cancel out, and we're left with inches. So that's consistent with our units of deformation, which is unit of length. So this inch squared will cancel out, these pounds will cancel out, and we're again left with inches. So once we punch this in the calculator, this first term should be 2.122 times 10 to the negative 5 times RA, plus the second term will be 8.488 times 10 to the negative 6 times RA, minus 0.1698. And I did a little bit of rounding there. But when we solve for RA, our RA should equal 5,714 pounds. Notice it's a positive value, so that means our assumed direction, which we assume RA to be in tension, a tensile force, is correct. So now let's find the reaction at C. So how do we find the reaction at C? Well, if we look at this original diagram, we can do the sum of the forces. So we have sum of the forces in the X. So if we look at the original, I'm just going to redraw it real quick. Here's the original. So this is RC, this is RA, here's 10 kips, here's 10 kips, these are both kips, kips. So we can do sum of the forces in the X direction. This is positive. So we'll have minus RA plus, I'm going to change 20 kips to pounds, so multiply 20 by 1,000, we'll get 20,000 pounds, plus RC is equal to 0. So we found what RA was here, so we can plug that in and solve for RC. And RC should equal negative 14,286 pounds. Oops. And this negative tells us that our original assumed direction is incorrect. So this RC we assume to be in tension is actually going to be a compressive force. So we had originally assumed that it was going to the right, so now the negative tells us that it's going to the left. So we found RA and RC. Now we have to find the normal stress in member AB, which again, if we look at the equation, is the force divided by area. So PAB divided by A, the cross-sectional area AB. PAB is equal to RA, which is 5,714 pounds. 14 pounds divided by pi over 4 times the diameter of AB squared, which the diameter is 2 inches. So this is inch squared units. So this should be about 1,819 pounds per inch squared, or PSI. So we have normal stress AB, and the stress in BC is going to be the axial force in member BC divided by the cross-sectional area of BC, which we found PBC to be RA minus 20 kips, which we solved here. So that's negative 14,286. 14,286 pounds divided by pi over 4 times the diameter BC. Diameter BC is 3 inches. So 3 times 3 squared, inches squared. So this should come out to be negative 2,021 pounds per inch squared, or PSI. So again, this negative sign is going to tell us that this is a compressive stress, and this positive value tells us it's a tensile stress, which also corresponds to the tensile force in the member, and the negative sign tells you that it's a compressive force in the member.